Hello everybody, getting ready to do lesson 10.2 part 3 today, pre-calculus math. Have those sheets out in front of you, and there's 0 points on your notebook for part 3, 10.2 vectors in space. And you got 18 points on your classwork sheet, name, date, period, due dates for other students. And now we're going to go right into example 7, solving an equilibrium problem. A weight of 480 pounds is supported by 3 ropes. The weight is located at S. Here is your weight right here. Here is point S right there at 0, 2, and then -1. So this would be a coordinate system here, 3D coordinate system, 3, 2, -1. See, here's, see, 3, 2, so it would be X would be 3, and then 2 would be our Y, should be out here, 3, 2, and then -1, so it drops down -1 on our z-axis here, so that would be the coordinate of that. So the ropes are tied to the points P out here, and then Q would be out here, 0, 4, 0, and then R would be -2, 0, 0 here. So you have 3 ropes here. Find the force or tension on each rope. So we need to find the tension on each one of these ropes. Okay, so again, here is our diagram. The downward force of the weight is represented by the vector W equals 0, 0, -480. So our force here of the weight would be -480. Which would be the negative force here on our for our Z position here. The force vectors corresponding to the rope are as follows. So here is our force vectors here will be 2 minus 0, 0 minus 2, and 0 minus a -1 over 3, which would equal our direction vector here of u would be 2 over 3 minus -2 over 3, and then 1 over 3 from this combination up here into our component, our vector component for corresponding to the ropes here. So this would be what we start with there, and then we go into V. So by again starting point for up here for our V will be 0 minus 0, 4 minus 2, and then 0 minus a -1, and then we end up with this component form of a vector for V. We got one more left to do, and so our component form of Z, when we again comprise our component here, would be -2 over 3, -2 over 3, and then 1 over 3 for Z here, which is this part of, which would be this rope here. For the system to be in equilibrium, it must be true that U plus V plus C plus W equals 0, or U plus V plus Z equals a -W. In this case, this yields the following system of linear equations. So to get this system, here's our system here. So basically what we have is we have a matrix here. These are component forms of vectors started out by the 480 force here. This -W, or rather the -W becomes 480 now. So we have a positive in this column here. So by using matrix manipulation that we've studied in chapter 7, you can find the solution of the system to be, so in this case U will be 360 with this here when we plug in our values here for U and V. And then V will be 36.7 for our V direction, and then for Z it'll be 360 would be on our Z part of our equilibrium, 360. Okay, using matrix manipulation to get those numbers. So the rope attached at point P, which is here, has 360 pounds of tension. The rope, so this rope here would be 360. The rope attached at point Q here will have about 536.7 pounds on it. From here to here, 536.7, and then the rope attached to point R has 360 pounds of tension by using those same calculations, by using that matrix. So knowing this technique, say for example we have a round bird bath, weighs 10 pounds, this would be it here. And then this would be a model of it here, put into a 3D system here. It has a radius of 12 inches and is supported by 3 equally spaced 30-inch chains. So 3 chains here, 30-inch, attached to a tree branch, which would be up here. Find the tension on each chain. So using that same technique that we used before, Q1 will be 0, -12, 0. Q2, which would be this one here, would be 6 times radical 3, 6 and 0. And then Q3 out here will be -6, radical 3, 6 and 0. And then P will be 0, 0, and then 6 times radical 21, which is up here. This will be on our, again, our 3D matrix system here. Our 3D coordinate system here. And then, so now we have the vector PQ1. When we put these two together, we come up with a component form of our vector now from combining this with this, and then down here with this with this, and then this with this. And then we come up with these component forms of our vectors. Once we have that, then we're going to let F1, F2, and F3 be tension on each change, force on each change. Since force 1 equals force 2 and then equals force 3, well, there will exist a constant C. I'm going to set up a symmetrical system here now. So F1 will be C, C, and C times these 3 component vectors here. And then the total force is -10K equals F1 plus F2 plus F3. The vertical component K satisfies -10 equals a -18, which is what we add these 3 together, multiplied by 21C, and then this, when you calculate this out, C will equal 5 times, or rather 5 over 9 times radical 21. And knowing that number there, we can now use that in front of each one of these components here, vector components, and then come up with these numbers out here. And then when we calculate these out, we'll have F1 equals F2 equals F3 will equal 3.64 pounds when we go ahead and set that up in a symmetrical system. So we end up with 3.64 pounds on each one of these chains. And that is 10.2 part 3 lesson, pre-calculus math. Questions or course materials, email me at animatedpowerpointmathvideo@aol.com. Thank you very much.